Well, let me start by apologizing for not being able to speak Russian. And it's been great to hear of all the work that's been happening here with Wolfram Technologies. And so I've come to try and share what we've been working on for the last couple of years to move that forward. But before I show anything new, let me try and put into context the way I see Mathematica and Wolfram Technologies. And the phrase computation everywhere is the thing that's leading us at the moment, is to try and find every kind of computation and bring it together in an automated way to make it available for anyone in any context. Well, that's a sweeping sort of vision statement, but the way we do it has been led for many years by a small set of key principles that we believe in throughout. And I helped write this list back in probably 2000, and it hasn't changed in the last 10 years, that everything we do, we believe in automating as much as possible. We don't just give you algorithms, we try and automate their application. We don't do toolboxes, we try and make one thing where everything fits together. We believe in symbolic computation, but not just computer algebra, a mixture of numeric and symbolic, the best way to solve problems, whichever that is, or whatever combination that is. We've taken the language very seriously for a long time. And in slightly more recent time, we've been trying to integrate knowledge. So it's not just computation, but facts about the world, economic data, everything you need to inform the computation. And we've always had this document-based workflow around the Mathematica notebook, which I'm presenting in here. And I hope you'll see that in the new Mathematica 10, we've stuck to these principles. So I have an hour, so I'm not going to show you everything that's new in Mathematica 10 because there are 1,000 new functions and probably quite a lot more functionality. So I've got enough time to show you maybe 100 or so of the things I think are most interesting. But very shortly we'll release Mathematica 10 and you'll be able to see all the other features that I'll be missing out. So we've done something for every area of functionality, every domain that we support, for image processing and for data analysis and statistics, for computer algebra. All of these areas receive something, but there's also completely new domains, and there's new ways to share Mathematica code and to make it useful than just the research and prototyping side. And despite all this, we always are mindful of how much there is to learn with Mathematica, and so there's more work to make it easier to use. So let me show you some things then. So one big important focus for us is on data science. In recent years, we've developed some very serious classical statistics capabilities. We have the biggest range of symbolic probability distributions of any system of software in the world. But there's more to working with data than the hard part. Wolfram Research always has this problem that we try and do clever things, and we sometimes forget the boring, easy things. And so one thing that we've done with this release is to make it possible not just to do the hard mathematical computations, but the more mundane getting and rearranging data in the first place. So we've got a new database-like structure that is native to Mathematica with operations that are for moving data around and rearranging. Let me show you. So here is the new structure. This is some data that I brought in. Perhaps this is sales from some company, and we've got years and how many units and how much revenue and who complained about the product. And it's not new that we can get this kind of data into Mathematica, but now we have the ability to transform it much more easily and elegantly. So I can start querying that data not just by the row numbers, as we have in the past, here row 1 through to 5, but by the named columns. So I don't need to know that this is column 4. I can just say, give me the complaints, the first 5 complaint numbers, the 0, 5, 6, 7 I've just picked out from here. And it doesn't matter if later I add a column at number 3 and this column becomes number 6 or 7 later. Name reference is going to be much more robust in code. And then we can use that mechanism to start doing all kinds of database-like operations, like drilling down into the data, rearranging the data. So here I'm selecting all the rows where the number of complaints is greater than 5, but I only want to see the units and the complaints value. So here's a new data structure drill down. I could do that before in Mathematica, but it was 3-4 lines of code and much less efficient. This is optimized internally to be fast with large data sets. I can aggregate. So here I'm saying not just selecting rows out, but totaling over the complaints, total number of complaints out of the data. I can do computations on the rows and columns, like what's the revenue per unit, and plot that as an aggregator. I'm saying I want a list plot of this calculation. And I can also take other data sets and merge them in. So here's a completely different data set. I've got costs, but it has something in common. It has a date column, just as my original data had a date column. So typical things that you can do very easily in SQL, but up to now very hard in Mathematica, is joining across references. So in relational databases, there might be an ID for the person, and you could join different data sets across that ID. Here, I'm joining across the date field. And so I've made a new data set where all the rows and columns are lined up. It works if there's items that are missing on either side. I can decide whether or not I want to drop those rows or show them as missing. And now I can do computations across these two different data sets, having brought them together. So this is a plot of complaints against the number of units shipped. And we can also do things like, here I've got dates by day, month, year. Well, I could group those only by the year part of that. So I can collapse down and merge those records by adding them together. And so now I end up with a revenue on an annual basis. So these aren't things you couldn't do before, but now you can do them quickly and computationally efficiently, and without having to leave the Mathematica system. So we get the data in, but we want to be able to do new things with the data as well. It's not just plumbing. We want to also do new kinds of computation. So one key area for that we've added is a new machine learning capability. So this is unlike the classical statistics, where you have in your mind a model that in classical statistics you might fit to a truncated Poisson distribution or have some idea of what the shape of the data is. Here we have data, but we know nothing. So here's an example, a new data table. And I'm imagining here that I'm a company selling investment products. And I know something about my customers, how much they earn, what occupation they have, and how educated they are. And then I find out what they've purchased, what kind of investment product they're buying from me. Now, there's no way I can tell whether higher income corresponds to more likely to day trade, or maybe it isn't. Maybe it's some weird combination of only high-income people who are not sales like to be long-term investors. Who knows? I don't have to care, because using machine learning, the computer tries to figure that out. So what I can say is we'll do the grouping that we did before. We'll group them by product. So here's all the customers who were medium-term investors. And then I'm going to classify that. So I'm going to try and build a machine learning classification that can then be applied to unseen data. And typical of everything in Mathematica, things like the method. There's, I think, 6 different machine learning methods that we've assembled, but I don't need to know. I can, if I'm certain that I want to use linear regression or nearest neighbor, I can specify that, but I don't have to. It can figure out for itself that here, naive Bayesian is what it thinks is the best way to classify this. And again, I don't have to care that some of these are numbers, some of these are categories, they might be other kinds of data. So now I can feed it a customer that it hasn't seen before, and it can classify that as its best guess that this would be a medium-term investor. And it doesn't matter if some of that data is missing, and there's all kinds of more information I can ask for. So I could ask for, for example, the probabilities to find out how certain it is that that person should be a medium-term investor, and it's classified that at 62%, with only a tiny probability that they'd be a day trader at 1%. So most of the interest in that is to take your data and classify it and then predict from it. But there are a few common cases that we've tried to build in straight away. And so, for example, we have a whole bunch of text classifiers built in that will take some piece of text, and it can classify that according to various topics. So it can figure out that that's probably an English statement, that it's something to do with technology. It can't figure out whether I'm male or female from that statement. And it seems like a positive, non-spammy, non-profane statement. Whereas if I say something like, make money selling Viagra, then it decides that's career and money, and it's oddly a negative statement, I don't know why, but that it's probably spam, and so on. Let's do one more. My name is Mike. Don't know why you picked Mike. Okay, so this is a good illustration that, of course, machine learning is not infallible. Mike is typically a male name, so it's misclassified that. I'm not sure what's misled it from the training set, but this is always, of course, the risk with machine learning, is they are all best guesses. Okay, so we can process the data, we can do some new things with it. We also need to get it into Mathematica. And so we have a new semantic import structure. So we have 180-something import formats for different kinds of data. But just getting the data in is only part of the step. The semantic import will take data and try and give it some meaning as it brings it in. So here's my data set, typical delimited text file with some numbers and words. And I'm going to import that as a semantic import. And hopefully, if it works correctly, it's brought it in as a table. And it's created these little yellow entity objects around the cities and the countries. And if I just pull out one of those, just to get the tooltip up here, we have this new object called entity, which is able to infer that this is a city. It says here, entity, city, Taipei City, Taiwan. So it's figured out that this is a city piece of information by looking at the general nature of this column, that these are probably countries, and then it's tried to figure out some of the disambiguity, that there are more than one, probably not more than one Taipei, but there's probably more than one Chicago in the world, and it's taken its best guess to infer the most probable location. And there's other ways that this comes up as well. We saw earlier the date object is now recognized, although when it was only given years, it couldn't tell if that was a date or just a number. So why is this useful? Well, once we have things as a kind of known entity, then we can start using the knowledge base that we've built up with Wolfram Alpha to start finding the properties on objects and the relationships between them. So for that Taipei city, there's all kinds of properties that semantically we know about. We may not have the actual data point for that particular city, but these are the kinds of relationships that are known about cities generally. And for a great many of them, we have data. So what we're starting to do is to expose the internal ontology of Wolfram Alpha so that you can compute with it, not just be a consumer of the website. And there are functions for interrogating these relationships. So I can take, for example, something like administrative divisions of France and find all of the ones that match that pattern, and hopefully if I get a little bit of data back from Wolfram Alpha, here's all of the départements of France. And that's, at the moment, is a first step, but the idea is that we can now build functionality on top of knowledge. And the first step of that, the first function that we've built, really built on top of knowledge, is a completely new geographics framework. So we can visualize information about these places and their relationships. So that value that I just took, the France departments that I looked up, I can now attach some numbers to them, here just random numbers, and I can visualize it, because we know about the shapes of the département of France. If it's built-in data that we're accessing, then we can actually provide the data itself from Wolfram Alpha, and here's a visualization of the population by département. And so with knowledge about, at sometimes quite detailed level, we can visualize any data related to places now in quite a rich way. So this works, for example, at a country level. Here I'm saying some values associated with countries. That Germany, I don't know what these values are, I made them up, but that Germany has the value 2.2, and so it's plotted that on some kind of orange scale, and I gave Russia a value of 5, and so that's colored differently. And I haven't specified the rest, so it's just given me a background to give it context. And of course, like all graphics in Mathematica, we have huge control. So I can change the background or the coloring format of images. So here I've taken the countries in Africa, and I've colored them according to the flags of those countries rather than against some continuous scale. Or I can overlay other graphics primitives like lines and arrows and arbitrary polygons on top of these graphics. So you can build up very rich visualizations to try and visualize information to do with economies or geological type information. Of course, there's a complexity with maps that the maps are not planar. We always visualize them as flat, but of course the world is not flat. And so, unlike other graphics, we have to be completely coordinate and projection aware. So, for example, if I show the route that Galino and I took to get here, then on an overhead projection, they look fairly like straight lines, but on a much more typical Mercator projection, straight lines on a sphere are curves on a map. And so that all has to be taken into account with all of these visualizations. Circles on a sphere are not circles on a map. So here are 1,000-kilometer disks around St. Petersburg. And obviously, once you get beyond the Arctic Circle, then things start to get a bit weird. And I guess this is the most distant point from here on the Earth. And as well as going outwards to countries and sort of world-level mapping, we can drill down deeply into the map information as well, so we have street-level mapping as well. So if, for example, I had gone for a walk with a GPS device around here, then plotting that would look something like this. Here I'm taking my data from the GPS device, and it's mapping those coordinates onto a street-level map with a range of 400 meters, and I'm overlaying the Mathematica, the spiky on top of where we are. Okay. We talked about sort of raw database-like data, but there's all kinds of other data that our technology supports. So one key area, for example, that we've supported for a long time is image processing. Now, in our numeric symbolic hybrid world, inside Mathematica, everything is symbolic, which means when we write a function that works on symbols, it works on everything. And so the machine learning fits into that category. Once we have machine learning for numbers and text, well, we have machine learning for everything. So I can take images now and machine learn against those. So here I've got photographs that have been classified against night and day. I do exactly what I did with the table of numerical data and say, classify that. I get a classifier function. In this case, it's chosen logistic regression. And then I can give it photographs it hasn't seen. And it can classify those automatically, that these 3 pictures are daytime and these 3 are night. It's had to figure out that shapes don't matter, but color schemes do. Another key extension on image processing is to build up more content segmentation and content recognition. So, for example, on segmentation, I can take pictures now and do things like remove the backgrounds from those. Has that? Oh, I haven't run that code. There we go. Remove background. So here I've segmented the foreground from the background based on the information that the background is vaguely light blue. And then I can recompose that image with new images quite easily. So I'm going to grab a list of entities out of Wolfram Alpha, cloud types, and I'll pick one randomly and overlay the image on it. And if I run that again, we'll get some other random choice. And things on a more practical level for business and commerce, on the feature content recognition side, we have things now like barcode recognition. So if you're building applications that need to be able to take QR codes and recognize them, then that's just another built-in native primitive. And lots of support for colors, and a big change to 3D image support. So I said we had 1,000 new functions. The function count is always very misleading, that in marketing it's great to say 1,000 functions. It sounds like a lot. But the 3D image support is an example where we've added a lot and there's no new functions at all. Because what we've done is we've extended 3D image support to handle all of the functions that already apply to 2D images, stretching and transforming, segmenting like background removal. I'm not sure if background removal is supported, but most of the segmentation functions now support 3D. Things like lining up images, detecting features, coloring them to be similar to each other, and all of these kinds of operations that worked only on 2D now work on 3D. So I can take medical imaging data like this. I don't know if this is medical or just some plant, but I can do things like morphological binarize. That says, find an object that is continuous and joined up that is brighter than the rest. So this is not a new function. It worked on 2D for a long time, but now we can pick out of this object, this hidden inside all of the detail underlying structure quite easily. And we also have throughout, which I'll mention again towards the end, support for many more little ease-of-use widgets. So if I'm working with 3D imaging and I select that now, we now get a sort of custom widget that only applies to 3D imaging that allows me to do things like live, real-time clipping planes, and I can change things like the color function on this to make it a bit more transparent in places. I never know what good values are for this. No, I'm ruining it, not making it better, aren't I? Oh, that doesn't look any better at all. So these are the kind of little things that we've thrown in to just try and make the workflow smoother and easier, so you can spend less time struggling with syntax and code to work with all kinds of different data. Okay, another new domain is computational geometry. Now, the simplest example I can think of to illustrate this is this very high school example, which is, imagine you have an infinite line that goes through 0, 0 and 1, 2. How close is the nearest point to the position 4, 5? I remember having to do this by hand myself on pencil and paper, and so we get out this nice sort of high school result. Now, of course, like everything we do in Mathematica, we're not just interested in numeric answers. We also deal with things like high precision answers. So if I knew this to 200 decimal places, we get the answer to 200 decimal places. And we deal with symbolic wherever possible. So if I wanted the nearest point on some parametric line, then I can calculate that very easily. But more importantly, we're not just interested in the simple examples like points near lines that you can do on pencil and paper. Whenever we tackle something, we try and develop it as far as we can conceive of this kind of geometric calculation going. So we have a whole set of primitives like disks and infinite lines and planes and half planes, and operations like unions of those things or the differences between them, so we can construct arbitrarily complex shapes. And then we can still do the same kinds of things like measuring them. What's the area of this shape? What's the center of gravity of this shape? And is a particular point a member of that shape? Now, I said at the beginning that we do numeric-symbolic hybrid, and this is essentially symbolic operations. The analogy of numeric, really, in the geometric space are discrete regions. And so I can take that region and now make a discrete version where instead of having these nice, elegant primitives like a circle, the whole thing is broken into the very simplest element that it's triangulated. And this, I think, is actually, in the end, the most important thing, because what it does is it allows us to work with real shapes. In the maths world, we try and make things simple. Everything is a perfect infinite line, or it's a perfect circle. And the real world is not nice, neat geometric shapes that we're used to. They're ugly, messy shapes. And by being able to discretize regions, then all of this geometry suddenly becomes useful to the real world. So the distance calculation I did before, I can now do that with a messy real-world object. So here is the coastline of Italy, and I'm finding the nearest point again. And the fact that it's not a triangle or a circle, but a messy map shape, doesn't stop me being able to calculate where I need to sail to if my ship is sinking when I'm out in the middle of the sea. It's the same fundamental operation, a region, the nearest point. And that also, of course, works in arbitrary dimensions, so many of these things work in 2, 3, 4 higher dimensions. So here's a 3D example. It's exactly the same computation, but this time I'm taking a 3D object, in this case my face, and working out where the nearest points from a set of start points are. And obviously you can see my nose sticks out a long way, so lots of the points lead to my nose. But in terms of how we describe that to the system, it's almost no different than nice, simple high school examples. I've just taken a graphic, which I've imported, and then I've turned it into triangles so that I can work with it as a geometric region, and then I'm just doing the same region nearest that I did with this map here. All of the complexity of dimensions is something that you shouldn't have to concern yourself with any more than necessary. So, we've got this concept of regions now, and at first glance it seems like it's all to do with geometry. But if you think more abstractly, this is simply a way of describing a space or shape in some possibly not even Euclidean geometry. They're simply sets of points or continuous spaces within a metric that can be described, which means that they actually are much more abstract than being about geometry. So we can apply them in all kinds of computations now. This is now a fundamental primitive within Mathematica. So we can take things that we could do before. Here's a contour plot of temperatures that I took last night across the region. And up to now, a lot of things in Mathematica are rectangles. When we do a plot, it's by default a rectangle that we've got a latitude and longitude with intervals which represent the rectangle. And that's very constraining. We're so used to it because it seems like a natural constraint that it'll take a little bit of adjustment to get used to the idea that now instead of plotting over an interval, I can plot that latitude and longitude over a region. And here the region I've got is to pull out the map of Russia. So by plotting it only over the region that I'm interested in, I get a graphic that is much more understandable because it gives us the context of where these various points are within that region. So all of the graphics commands take that now. It's not so useful, but if I want to, I can do a 3D plot of that same information and get, hopefully, here we go, a 3D curve where the outer region is the map and the heights are the temperatures. Okay, I've got the aspect ratio a bit messed up, but you get the idea. And it's not just visualizations. As many computations as possible make use of regions. So if I just do a simpler region here, which is again this sort of union of shapes, actually it's a slightly different one, then I can do the 3D plots we just saw over it. But we can also do computations like what's the lowest point on this region. And so the constraint of staying within the boundary is just automatic. I just say minimize a function over the region. So there's the lowest point. It's a bit more complex than I thought, so let's make a numerical version of that. So the lowest point is at minus 0.3 plus 0.9, so about there, I guess, is the low point. We can find things like integrals, again, over the region. So I can just say, give me the integral of that function constrained over this region. So it's two-dimensional, but it's missing out the whole, and it only goes up to the edge. And all kinds of other things are supported. And one of the biggest areas, and certainly the hardest, has been to extend that concept of computing over a region into differential equation solving. So for the first time, we have a full finite element system within Mathematica for partial differential equation solving over arbitrary regions. So that means I can do something like take in some 3D geometry and then just use the ND solve that we've had for many, many years that only worked over rectangular regions and say, I want to solve Laplace's equation, and I've got some horrible, complicated boundary condition, but plotting it where x, y, and z are over that region, and then we'll visualize it. So there's nothing any more complicated than ND solve, apart from the boundary condition, which is a bit messy in the equation you have to look up. But all we have to say now is instead of over a rectangle, we can solve this PDE over a 3D geometry. And so here I've got this 3D space shuttle shape, and I've solved effectively the heat equation over that shape. So this has taken years of work to get right, and it almost does it no credit by just hiding it entirely automatically behind NDSolve, so that you're using exactly the same command as if I'm solving some trivial ordinary differential equation. But behind the scenes, it's triangulating the mesh, it's forming a finite element framework of the equation, and it's solving it over those boundary conditions. Quite a rich piece of work. And so here's the region I had before. This takes about 20 seconds to run, so I've got it pre-generated here. But here's solving the wave equation over that weird region that we optimized before. And so if I animate this, we get to see how a wave would propagate if released in a weird tank of water with an island in the middle of it. But again, it's just differential equation solve, the wave equation, and somewhere in here it says x and y are elements of the region. Pretty straightforward. And I won't go through the code of this one, because this one is a bit more complicated. But here I've got a typical kind of engineering example where I've got a crankshaft for a car, and I'm discretizing it, and I've got the equations that represent stress. And at the end of that, what I can do is show the original crankshaft, and the red is the deformed. It's how it's bent under the stress. So it's still, to do difficult problems, there's still some work to do. There's a lot of specifying the problem, but it's right there in the system, and it's all made possible by this concept that now we can work in any shaped space, not just rectangles. So it's a really big change to Mathematica. Even though in finance the engineering examples aren't relevant, being able to constrain over the space that you're working in is much more powerful than having to worry about whether you've entered into things where the boundary conditions of your world would make the answer meaningless. Okay, completely different domain now, much more relevant within the kind of finance economic space is time series. So we have a new time series object to be able to work much more elegantly and efficiently with time-dependent data. So if I pull certain data in from the example I started with, my sales data at the beginning, I'm going to pull in the date and revenue. I now have this time series object. And you notice as well that throughout the system now we have these little sort of simplified views on objects that are too complicated to display. So where before in Mathematica it just said something's missing, and you had no idea what it was, now we get a little spark line, and you get some basic information about the time series object, like the time interval it runs over, how many points are in the set. So at a glance we can see that we're dealing with the right data. So there's a whole collection of things like merging and joining time series and transforming them. But in the end, it leads up to being able to do things like time series model fit, where I can take that data series and I can come up with a fit based on random processes. And again, automation as much as possible. So out of 6 or 10 times random process objects, it's figured out for itself that a Sarama process is the best process to use, as well as choosing the right parameters for it. So if I'm not an expert, all I say is, it's a time series, give me a fit. And from that, I can now take the original data in the blue here, and I can make a forecast based on this fit that I just created. So just like the way we could take linear regression very easily and extend from smooth data, now things that are seasonal, it's much easier to make seasonal future projections using the high integration with other processes. And we can do things like simulations from it as well, because this fits in with that whole framework for random processes that we added in Mathematica 9. So here is a simulation of 100 possible outcomes from the data, from which we might look at things like the distribution or confidence bands. So there's lots in this new framework. There's hidden Markov processes, which are quite important. I don't have time to show examples. New significance tests for time series data to know whether they're autocorrelated or whether they appear to be significantly autocorrelated. And transform time processes so you can do things like stretching and shrinking and merging different time series together. Okay, another completely different domain, graph theory. And another domain where we've done a lot without adding very much in terms of functions, because the main news here is that we now have support for mixed multigraphs. So those are graphs that contain edges that are directed and undirected in the same graph, and graphs where some points are multiply connected. So we have lots of graph theory functionality, but up to now they either had to be directed or undirected graphs, and they could only have many of the operations only worked over graphs that had single connectivity between vertices. So to leap back into the trivial, it now means at last we can solve the 7 bridges of Königsberg problem, which is, can you walk around all of the islands crossing each bridge only once, which in our space is just a case of declaring the graph and then asking whether that's got this particular property, whether it's Eulerian, and it can't be done. But of course, again, our aim is always to scale to real-world problems, and so there's been a lot of work in making sure that this stuff scales up to very large graphs, whether those are social networks or transportation optimization, including, I believe, I'm told, we have now the fastest implementation of the traveling salesman problem in the world, and one that also works over graphs, not just completely connected graphs, which is the sort of classic solution. So there's a whole bunch of new operations that do go with these, things like tours and paths. So here's sort of classic simple problem. I've got areas in a supermarket distribution center that we need to connect with conveyor belts, and there are costs associated with the connection. So I want to work out how to connect everything up at the lowest cost. Well, that's a fine spanning tree problem, and so here's our minimum cost connection. And of course we could do things that we've been able to do before on these mixed multigraphs, like what's the shortest path from a particular station to another, taking into account the cost. What's the shortest tour to join all of them up? This is the traveling salesman problem. And what's the flow across that network? Here's another one which is new, which is vertex-independent paths. So the classic problem here is something like a multimedia distribution system where you've got clients and sources, but they crisscross between them, and we need to worry about routes that can't fail, that if a vertex goes down, then what alternative routes are there that don't depend on that vertex. So it turns out there's 3 solutions to go from this source to this client, one through this route, one through this route, and one going all the way across here. But this isn't a solution going back this way because it shares a common vertex with other solutions. So there's all of these new primitives for working with these graphs, but the graphs are very abstract. They don't care whether they're road networks or telecoms networks or social relationships or biological networks. They're just abstract graphs as far as we're concerned. Oh, I thought I'd missed something. Actually, I won't say much on this, but we're also extending all of the other domains like sounds and signal processing, where we can now do much better sampling of things. We can filter and analyze sounds directly. One that I think is useful because it's not just to do with sounds is peak analysis, where we have a bunch of fairly generic primitives now for being able to find peaks. So here is the peaks of the sales data that we saw before. Fairly easy to see by eye, but often a little bit of a pain to get out programmatically. And now we just have a generic find peaks command that gives some tolerance. If I turn this tolerance down, we'll pick out more peaks than we want to. So we start getting the small peaks, and I guess at some point we'll get every little peak. So you set the tolerance, and then it picks out peaks for you. It's obviously useful for signals that are in any space, not just in sounds. Okay, so there's lots of computation. There's always lots of computation in our technology. But we're not just concerned with the kind of prototyping, problem-solving end of technical computing. We want to be able to build things on top of it. We want you to be able to build things on top of it. In the end, we're a platform. We don't do anything, any final end solution, apart from if you think of this as a glorified calculator, but what you can build on top of it is what makes it relevant to end users who don't care about all these computational functions that might be going on inside. So we've extended the language, and we started talking about the Wolfram language in its own right, because we have a range of products about to come out that will be driven by the same language. And with that, we've extended the language with much more functional programming, lots of new convenience functions just to make software development quicker and easier, and more control over evaluation. If I want to let only part of a computation evaluate, I can now do that rather than the all or nothing that you have now. And software development tools like testing tools that up to now were only available in the Wolfram Workbench are now available directly within the language. Somebody else is talking about language later, so I'm going to skip this completely, and you can wait for his talk. But you can write programs, and the programs can be powered by computation, but in the end, there's a deployment. I need to share a program. Unless I'm the only customer for my program, the only user, then I need to be able to get things out. And there's lots of different ways to get things out of Mathematica. One is the document-centered interface that I've been using, which is, in the end, is about writing reports or academic papers or dashboards for data. And for a long time, the documents have been programmable. I've got commands like notebook and cell that allow me to describe a document using the symbolic language. But we've got a great way of making documents, which is the Mathematica front end. I can type things, and I can select these cells, and I can change their style and reformat them much more quickly using menus and keyboard shortcuts than I can with programs. So what we've tried to do is to bring the two together, the ability to programmatically generate, but the ease of authoring that you get through the front end, and that's report generation. So the idea is that I can have a template. Here is my template. I've created this by hand, and I've created cells, and I've been able to tell bits of the content that they're not the final content, but they're going to be filled in later. So here I've got a field that says author, and it's got a default value, which is John Smith if I don't provide it, but I'm expected to provide that later, and other things that will fill in automatically or be computed. So the idea is then I can take that template, and I can provide the information at the time that I create it, so I can now call up that template and populate it. And here is a document that I've just created programmatically. So I didn't have to know anything about cell styles, or if any of you delve into this stuff, things like style box and make boxes and all of these kind of low-level commands that you can do this stuff with. I just create a document, mark up the bits that will change, and then call it as a template. And we have templates in other fields like XML templates and text templates and so on, but the CDF is the main one. Now, having created that, so this is great if you've got the same report that has to happen lots of times, but the data changes, or you want it live like a dashboard. It's still easier if you're going to do something once just to write the thing by hand, but if you're going to do it several times, setting up a template saves you time. But we also need to get those things out there into the outside world. And we've had the CDF player for a few years now, where you can take the Mathematica document and let somebody who doesn't have Mathematica open and interact with that. But there's still barriers with that. The CDF player is 100 megabytes of download. Not huge, but something you have to wait a couple of minutes for. Some people don't have admin access. They can't install software because their computers are managed by other people. And some people simply won't download plugins. So we've come up with a new deployment, and I'm switching here out of Mathematica into a web browser. So I'm only in Firefox, no plugins. I'm just using a browser just like any person could, as long as they've got a browser made in the last 5 or 10 years. All I'm using is JavaScript. And what we have now is a mechanism for rendering these things in the cloud. And if I browse here through my files here and open a CDF, then all being well, here's my CDF, and it looks just like a Mathematica document where I've got cells which can be grouped, and I've got graphics, and I've got narrative text, and somewhere here I'm going to have a manipulate, so I can change the parameters of this piece of code and interact with it entirely in the browser. And so now for the first time we can take these great, rich, and computationally interactive documents and share them with anyone with no barriers at all. And more than that, I can actually do Mathematica in the cloud. So if I, let's do a new document here. It's not just rendering CDFs, it is Mathematica in the cloud. So I can do, well, let's do something different. Let's do a plot 3D of some function. And I can type straight into the browser. I should have picked something simpler. And I can hopefully compute this in the cloud and get my answers back in the cloud. And obviously this is being worked on live right now because I ought to have got something back straight away. Got it back eventually. So here's my plot, and I can even do the kinds of things you're used to in the front end where I can resize these things and rotate them, and it's the full experience. It's the full language, and this is a CDF. It's not just a conversion of the CDF. If I download this to Mathematica, it'll open the same. I can edit it in Mathematica and push it back up to the cloud. So, of course, we want to streamline that process between cloud and, let me just recreate that document here, and the desktop. And some of this you can do manually. So under here I've got, okay, grayed out for some reason. I probably haven't logged in for my Mathematica. I've got open from the cloud and saved to the cloud. But I can also do that programmatically. So this report that I just generated, I can just deploy straight to the cloud, and we've got permissions, so by default things are private to me. But by saying permissions goes to public, then what I should get now is, maybe I should have logged in. Oh, there we go, a cloud object. So I can do things like deleting that file from within Mathematica. And if I go to that URL now, then we should find, here's the CDF that I just created programmatically for my desktop, available to you right now. If you went to this URL, you would be able to see this CDF because I made it public. So this is great for being able to do things like automatic reports that run overnight, automatically deploy out to a specific URL so that your users can come in the morning and see them and interact with them. And if we go back to the program cloud, we'll also find things like under deployments, we have things like scheduled tasks here as well within the cloud. So within the cloud, I can set things up to run every hour or every 12 hours or whatever without me having to have my computer running. It just is left running in the cloud on a schedule. And these files, of course, mean that you can go anywhere and your files are available. All of those cloud benefits that we're used to from things like email, you can set things up so that your colleagues can edit the files, so you can collaborate over the same document, and you will always see the latest version, and there's a version history. It's a really rich cloud deployment. Now, the one way of looking at that is it's just computation everywhere. So I can run it on the desktop or in the cloud. It depends whether I'm on the move or at my home station, which is best. Things are faster locally because there's no internet latency, but they're more shareable in the cloud. But they're sort of the same thing. But once you've got the cloud, other things start becoming very easy. And APIs and forms are really the sort of the key two things here. So we've got a whole new symbolic language for forms, first of all. So here I've got a form function that takes two things, a value and an email address, but I've restricted what's allowed in the form. So the one first has to take a number from 1 to 99, and the second one has to be an email address. We can just test that form here in the front end, and let's put in a value and an email address, and it says, well, the number works, but that's not a valid email address. Maybe I'll change the number here and submit, and you see now it's rejecting something else. And this is all part of this semantic language that once you have a concept of what things mean, then the idea of that an email address is an email address is a kind of known concept, and that's all part of the entity system. But once I've got this sort of form function, then cloud deploying it becomes much more meaningful. So I can take that form, and what it does is it takes the value that I entered and makes the factorial of it. In fact, let's just do that now so you can see. If I do the factorial of 10, I wish I had not asked for the email address now, since I have to type it. And there's the answer. I can now cloud deploy that form, and it just in the same way that I pushed a CDF to the cloud, I now have a little mini application in the cloud. So the form is right there for anyone to access, and I can type in my numbers and my personal details and submit it, and the computation has been done in the cloud. It's a rather simple computation. I should have put some pretty formatting and made it big and colorful or something so it looked nicer, but all I did was return the value here. So if you want a user to be able to go and access your computation without having to access code, you've now got the CDF for making things with manipulate and sliders and buttons, and you've got forms. But there's another key direction, which is your user isn't always human. So sometimes we want computational services to consume your computation. And so we have an API function equivalent to that, which says it's going to be an integer, again it's restricted, and it's going to take that number and add 3 to it. But I'm going to deploy this as an API. So again, we have to push this out to the cloud. There's my cloud object. And if I go there, it has failed, and it's failed in a very unattractive way. That's what it should have looked like. Because I haven't given it the parameter. So in order to use that as a RESTful service, I have to put a parameter on here which is x equals whatever the number is that I'm going to have. And now when I evaluate that, it returns the computation. So constructing this URL, of course, is the job of your client service. And so you want your program to be able to call this service so that your computation is then accessible, and you can, so that you don't have to deploy Mathematica to the end user. So one typical use case might be, supposing your end users say, yeah, Mathematica is very clever, but I'm not using it. I want my stuff in Excel. Okay, well, Excel's never going to do the kind of computation that we can, but now what we can do is deploy a service out to the cloud, and then we take that API, and we say we want some Visual Basic code for that, and we can generate a Visual Basic template, which we can then put into the Excel spreadsheet, so that when you access the Excel spreadsheet, without you knowing, behind the scenes, Excel is calling the cloud using this piece of Visual Basic code, and then the cloud is returning the answer, and Excel displays it. So the end user sees Excel, but you've done the job in a language that's actually capable of doing things. And there's all kinds of languages supported here, so I could say, for example, deploy that to Python, or there's half a dozen different languages. Python looks a bit simpler than Visual Basic. Of course, in the Wolfram language, in Mathematica, calling services is extremely simple. So all I have to do is take the URL and do URL fetch. So it's the shortest solution of the lot. I just say fetch that URL with the parameter x goes to 14, and now I'm consuming that remote service. We don't need to see the details of the transaction. We just say call the service with a value, and we get the answer back. Okay, a few more things on software development. So another key thing is integrating into existing services. You can create your own, but there's all kinds of useful services out there, and we've started a new framework to include those. So, for example, I can connect here to my Dropbox account, and I can immediately interrogate things to do with Dropbox and say what's the information on who I am, what's the file names within my Dropbox root directory. I can write files to it and read them. So it makes it a lot easier to integrate in with those kinds of other services. If you're doing automated reports, then one thing you might want to do is to alert yourself to the fact that the report's finished running if it's something slow. So there's a whole set of messaging services built in. So, for example, I can connect right now to Twitter. I can find information on my Twitter account. As you can see, I'm not very popular, since I only created the account last week. And then I can, let's just grab an image here, if I can wake my webcam up. Oops, webcam did not wake up. Try again. There we go. Let's do something with a slightly more dynamic pose. Oh no, I'm not sending that. Right, that's more like it. So now connecting in with the real value of the service of being able to read information from it and write information to it is just as trivial. So I simply say, execute on that service, the service connection that I created, and I'm going to do an image tweet, and I've got some text, and I've got an image which is that. Actually, I'm not going to catch another live one. Let's send the one that I've just created. And so now I've just, hopefully, there we go. I've now tweeted. If anyone's following on Twitter, then you'll be able to find that message now out there sent programmatically from within Mathematica. And the reverse direction of analyzing tweet streams and doing things like machine learning on them or semantic analysis is just as easy. And at the moment, the service list is quite small, but we hope to add to it. So we've got things like Facebook and Google+, Instagram, LinkedIn, mostly social services, but also the beginning of connection to things like services for keeping fitness data. Which leads me into devices. We've had this project for a little while, which seemed a little not like us, a project to curate and collect information on the Internet of Things, on devices, jogging meters and oscillograms and all kinds of just physical things. The reason for that is what we're starting with Mathematica 10, which is the ability to do things like device control. So we have, just like everything, we've tried to reduce down to a minimum set of concepts what it means to connect with physical devices. So I can do things like look around and find what are the devices attached to my machine, and I can find a camera and some demo devices. And now, let's just try the most dangerously live part of the talk here, which is let's see if I can connect to a physical robot device here. And the Bluetooth on my machine is very flaky, so there's a good chance this will not work as I look for the device. It sees it. Will it hold a connection is the question. It is holding a connection. So having set that up, I can now do a device open to connect to that device. Yes, I suppose I do want to run it. And I'm going to try and put it so that you can see the thing on the floor here, but we'll see if... So we've got a connection to that device. If I just fire up a webcam here so that... we can see it. Ooh. Okay, I'm going to have a hard time typing while showing this, but so I've got this small robotic device, and I can start doing things like reading. Oops, something went wrong there. I can read the device's ASCII name. Come on, talk to me, device. Okay, well, that's not going to work. It doesn't want to tell me its name. Have I lost connection? I may have to abandon this. Oh, it's gone and lost the connection. Yep, and now that's why it's failing. Okay, I will give that up, and anyone who's interested, I'll try it over lunch. But yes, my Bluetooth has dropped out, so Mathematica obviously can't make a connection without the Bluetooth. So let's just skip over that. The basic idea is that we have primitives for reading and writing, so what I was going to do was to write to the device an instruction to roll across the floor at a particular angle and go around in a square, and I've got a little widget to control it manually. The key thing here is to build up a set of primitives so that we can capture things from the real world, that if I have experimental devices running, capturing experiment data, I can read it straight into Mathematica Live. If I'm gathering data about the way people behave, I can capture things directly from the devices, and that will work also through the cloud in many cases. So that means that we actually have a real tangible connection to the physical world, as well as now being able to describe the physical world through the geometry setup. And with that comes things that are needed for robotics, such as integration with System Modeler, our tool for controlling things, new control theory, and also key is embedded deployment. There's nothing to show here, really, because it's the same thing. We can now run Mathematica on the Raspberry Pi, this $20 computer, and it's running a full Mathematica. Intel Edison are coming out with a SD card-sized computer that's a full computer. We'll support that too when it ships properly. And this means now that you can take your code and you can actually put it in a device. So if you're building things for the Internet of Things, the Internet of Things does not need to be the Internet of Stupid Things. It can now be devices that have enough computation on board to have intelligence and to work things out about their environment, to feed back to the cloud intelligent information or pre-processed information, and it's sort of extended our idea of compute everywhere. You might write on the desktop, but you can push into the cloud, or you can push into a real object that people take away and use. And the days where you had to try and generate C code that ran on sort of cheap embedded chips is going to fade away in favor of proper computers. Okay, so that just leaves me in the last couple of minutes to talk about ease of use. I said that we'd made things easier. I'll just run through a few things here. The predictive interface, I've got it turned off because I know Mathematica by now, but that's been improved, of course. There are new kind of automatic templates so that if I type something here, I get automatic completions as I type now. And if I can't figure out what the templates are, they're right there on a click away as well. Say, here's the typical usages of that command. So trying to reduce the amount of things you need to hold in your head. The auto-completions have been improved, so we now have option values completed. So if I want to put something like plot style here, then it knows some typical values that I might want to have on the right-hand side of that. So dashed or whatever, or a new one, plot theme, which gives me sort of various automated themes already pre-built. So I can pick detailed there and see kind of detail plot. Strings now autocomplete, so if I type something that has a string argument that is known, that autocompletes. Things like methods are all part of the string completion. And also some of these things have GUIs or completions that give me a direct visual hint. So if I wanted to style some text and say font family, you can see that I'm actually getting the kind of pre-formatted fonts to show me what the font might look like when I've used it. And let's try Bauhaus 93. And if I wanted to do something like font color, then here's an example of, so it pre-fills in with some suggestions, but I'm not going to do that. I'm going to do RGB color. And you see now it automatically gives me the automatic specialized GUI, just like the image processing, where I can click on that, and something went wrong there. And now I get a GUI to, I missed the arrow, but it gives me a GUI to be able to choose the color by hand. There's improved formatting. Here's a typical problem that everyone's had, which is you're editing text, and we do some fabulously complicated computation like 2 + 2. And you get the answer 4, and we go back and edit it, and it no longer corresponds to the answer. We forget to reevaluate it, and we've got an input that doesn't match the output. Well, that now grays out automatically, so you can see you've got out-of-sync inputs and outputs. And it's only when I reevaluate it that it goes black, and we can see that it's correctly done. And last but not least, we finally have proper multi-level undo. So you can undo back through the full stack of computations and inputs and outputs that you've done. And while it's been late in coming, we at least try and do these things right. So you have control over things like, if I ever manipulate, is the slider movement undoable? Or which slider movement is undoable? There's full specification for how undo works, but it's been I know we've all been waiting for that one. So I'm out of time, so let me just summarize again what we've been up to. Huge amount of new functionality, but it's about both extending every domain, including some almost invisible things like performance improvements behind the scenes, but also trying to fill out this automating all of computation into one environment, finding those domains that are not yet covered and including more of those, and as fully mapped out and as widely applicable as possible. And new ways to deploy work. So when you write something in the Wolfram language or Mathematica, you can make it useful to other people more easily than before without having to worry about those issues of do they have the same tools. And hopefully we've seen all through that the long-standing principles are still there, that when we add an algorithm, we automate the choice of the algorithm. When we add functionality, it's right there connected and interconnected as much as possible, that machine learning is connected to every function, not just some separate little toolbox that only lives in its own right. That we do everything numerically and symbolically wherever possible, and that as much as possible we bring in things like Wolfram Alpha so that that knowledge is integrated into the system. And we've taken this idea of document-centered workflow even further by pushing that into the cloud. So it's now document-centered deployment and document-centered collaboration. So I hope that this is going to all be very useful to you. And it is not, I can't give a date, but it is in the weeks, not months state at this moment. So pretty imminently we'll be letting you know when you can get your hands on this. And I give you Mathematica 10. Thank you.